All right, let's get started. So hello everyone, my name is Caleb Choban. I'm a postdoctoral fellow at Indiana University Bloomington. And today I'm going to talk a lot about dust. We're going to talk about how we model dust evolution from cosmic dawn to cosmic dust. I was going to just talk about the dust, but I realized I've talked about, the dawn, but I was going to talk about the dust first because it puts it in context. Kind of a tagline for my research is I like modeling small things and big things, dust and galaxies. So, to talk about dust, I need to give an overview of dust observations and how we've used these observations in the present day to build up an understanding of the dust life cycle. So what do observations tell us? Observations tell us when we look at dust within galaxies, dust varies with local galactic properties. The strongest correlation we find is that the fraction of metals in dust, or dust to metals ratio, increases with density. So you have more of your elements locked in dust as you go to denser regions of the Milky Way and large and small Magellanic Clouds. There are other significant correlations, but they're relatively weak in comparison to this. So more dust in dense regions. When we look at dust populations between galaxies, we find that they vary both in the amount and in their composition. We find that the galactic dust to metals ratio and the fraction of your dust mass in pause, or QPOS, both decrease as you go to lower metallicity systems. So less of your metals are locked in dust when you're in lower metallicity galaxies. And when we look at extinction curves, we find a change in chemical composition, mainly this 2175 angstrom bump that's due to small carbonaceous grains. Milky Way is a very prominent bump. The bump weakens in the LMC and is practically non-existent in the SMC besides a few sight lines. That's telling us there are less small carbonaceous grains as we go to the LMC and SMC, so the composition of our dust is changing. And when we look at very high redshift, these observations of extremely massive dusty galaxies at redshift 5 to 8, with things like the Rebels and Alpine survey, tell us that dust, or galaxies, may be dust-rich for almost their entire lives. So with all these observations, we built this understanding of the dust life cycle. First, dust is created, mainly in supernovae ejecta and AGB winds. These metal-rich ejecta, some of those metals condense, form into dust grains, and this is the start of our dust population in our galaxy. When our dust is hanging around in the interstellar medium, it can be destroyed by supernovae shocks. This is just to have a propagating shock wave. It's shocking the gas and destroying the dust as it travels through the ISM. This is believed to be the main destroyer of dust in a galaxy. Dust can also grow in dense regions of a galaxy via gas-dust accretion, where you just have these low-energy gas-phase metals colliding with the dust grains, sticking to them, growing them over time. This is believed to be the main producer of dust mass in the galaxy. Dust can also get destroyed by astration. This is just you have a dusty molecular cloud that collapses to form a star. The dust in that cloud is also destroyed, contributes to the stellar composition. And if your dust gets thrown out into the galactic halo, it's primarily just going to be destroyed by a thermal sputtering. You just have these energetic protons, electrons eroding the dust grains one atom at a time. Now this is our general understanding of the dust life cycle, but big old warning, there's uncertainties everywhere in each of these processes. Observations of supernovae creation of dust or orders of magnitude just from looking at 1987A. Also theoretical models, same way. We don't know how efficient supernovae producers are. We don't know how efficient supernovae shocks are either at destroying dust. Theoretical models give orders of magnitude estimates as well. And we can't actually test gas-dust accretion process in the lab. The environment's too extreme for us to actually try and test it in chemistry labs. So this is where theoretical models come in to try and test these uncertainties and look by comparing back with observation. So for me, I'm using fire. I developed this dust evolution model. Luckily, I don't have to talk about fire because I've already heard enough about it. I'm going to talk about the dust model. So originally in fire, there was no dust evolution model. So most of these simulations you've been seeing, the dust does not evolve. The dust is just a set fraction of the metals, about 40%, which we see in the Milky Way. But over my thesis, I developed a dust evolution model that was integrated into fire. And we ran a few simulations. So all the simulations you're going to see here are reruns of these older simulations. And the kind of main aspects of this model that make it so powerful is that we track the evolution of specific dust species with set chemical compositions. So we track carbonaceous dust, silica dust. Also, we have to track some theoretical dust species because we have to confront these major uncertainties in dust chemical composition. There are reasonings for them. We just can't really observe them. They're very hard to observe. But all of this kind of tracking of specific dust species is very important when you model these different dust processes, mainly things like gas-dust accretion. But the great thing about this model is also we can resolve when and where these dust processes happen because they're integrated into fire. So we can resolve where accretion happens. It only happens in cold neutral gas. We can destroy dust locally around supernova events instead of having to kind of average them out over the galaxy for like lower res simulations. And we also have kind of gone really deep into the dust physics. There's no real tuning. It's kind of the motto of fire. Try not to tune, just try to put in the physics, see what comes out. So we put in a lot of physics to try and understand the accretion process and all the different factors that can affect dust evolution, like phloem enhancement for gaseous accretion, carbon monoxide formation can affect the growth of dust as well. It's really no real tuning, just diving deep into the physics. But just batteries not included, warning that it doesn't model everything. Right now, it doesn't model grain size distribution evolution, which is important for things like extinction curve predictions. We have no explicit pop prescriptions either, but these are two things that I'm actually developing right now. Look forward to seeing those in the future. But I was going to talk about the main power of this model is that looking at reproducing present-day galactic dust population, how well can it reproduce what we see already locally? So for this, we reran a suite of Milky Way to dwarf mass galaxies. They're nice Hubble images of these galaxies. So mainly looking at the Milky Way, large and small Magellan Cloud observations. What we see is we can reproduce a lot of observations very well. Mainly, we can reproduce these galaxy integrated observations of dust to metals versus metallicity, and also local observations of things like element depletions in the Milky Way, large and small Magellanic Clouds. And we find that most local galaxies, their dust mass is dominated by the accretion process. We also have some other major findings that I just want to point out that are important for high redshift. We find that this rapid growth of dust by accretion doesn't turn on until you reach a critical metallicity threshold in your galaxy. And this critical metallicity threshold is different for different dust species. So carbonaceous dust grows later, at a later time than silicate dust. This is just due to differences in their elemental abundances, physical properties between these different chemical species, and also differences in their life cycles. We also find that the buildup of dust mass once accretion is efficient takes time, because accretion only happens in dense regions. So you have to cycle the gas in your galaxy into this dense region to grow your dust mass, and then back out. And so it can take an appreciable amount of time depending on the overall amount of your coal gas fraction in your galaxy. All right. I mean, we matched the observations, right? If I was maybe a lesser theorist, I would finish right here, right? Dust mission accomplished. We understand dust in galaxies, right? Right? Or maybe not. So I wasn't really satisfied with this because a lot of models can reproduce some observations at present day, but they have a lot of differences that kind of go back to that uncertainty in the dust life cycle. So we can use these observations of very high redshift, dusty star-forming galaxies to further constrain dust theory and also put the observations in context too. So just to kind of review, I don't think many people have talked a bit about these, but we have these ALMA observations of extremely dusty star-forming galaxies that have been observed in the dust continuum. They're on one band for ALMA. And so the information is relatively limited. We have a stellar mass, a dust mass, star formation rate, some other ancillary stuff. So these are kind of the main things we have. So we see we have these very massive, very dusty galaxies. JWST, though, is going to provide us with more information, mainly the metallicity, which I'm really excited about because metallicity is so important for dust evolution. It also breaks some observational biases as well. This is really great for testing dust theory because we can put better constraints on the accretion process and supernovae creation. Because the universe is so young, galaxies are so young, is that enough time to build up our dust mass? Is less than a gigayear enough time to build up these extreme dust masses we're seeing? And also the other thing is that at present day, supernovae creation of dust is very subdominant. It's less than 10% of the dust mass in our galaxy. That's like an upper limit, I would say. But it's probably a more significant source of dust mass at very high redshift. Sorry, this should be, yeah. So hopefully we can put better constraints on the supernovae type 2 mass creation. So I reran a suite of these high redshift galaxies that we've seen from Jason and Claude Andre. We're looking at just the most massive galaxies in the sample that are ending at redshifts of 5, 7, and around, this one's around like 10.4 when they reach their kind of end of the simulation. I just want to highlight some of the galactic properties that are important for dust evolution specifically. We've already kind of heard this story already. Mainly these galaxies are extremely bursty. This is important because dust grows in cold gas. And so if you're constantly evacuating the cold gas, you're going to stunt your dust growth even if accretion is an efficient process. It reached that critical metallicity already. So this will make accretion growth slower. Also, as Andy Marzawiski will talk about later, I think on Friday, the galactic metallicities for these galaxies are quite low compared to their analogs at present day for similar stellar mass. This is the cold gas metallicity for these galaxies, and the most metal-rich galaxy is around like half solar. So that means accretion is going to start later because of this limitation of needing to pass this critical metallicity threshold. And accretion timescales are just going to be longer because they scale with the metallicity. So it's already not looking like a good environment to build up your dust mass by accretion. So can we reproduce this dust mass buildup at high redshift? And the answer is our fiduciary model cannot. It falls flat on its face. We fall well an order of magnitude below any of the observations at any redshift at any stellar mass. That's pretty bad. And that's because accretion is very inefficient, as I pointed out. Starts too late and struggles against supernovae destruction because of this bursty star formation as well. And our model actually has kind of a low stardust creation efficiency for supernovae type 2. So that prolongs the buildup of dust mass because you start at a lower dust mass when accretion becomes efficient. But what we did is we ran this enhanced model, is what I'm calling it, where we enhance the accretion by about a factor of 4. That's within, I would say, uncertainty, because there may be some missing physics that we aren't accounting for, like subresolved gas pumping. And we also increase the supernovae creation efficiency well within the uncertainty from observations from theory. And we find that does help at boosting your dust mass by about an order of magnitude, about a dex. But it's still really not enough to match, especially these alpine observations and these Rebels observations at the lower stellar mass end. So the question is, what's going on here? Why can't we produce these high dust masses? So I did some, kind of back of the envelope check. Okay, metal, dust comes from metal, so let's put an upper limit based on the total metals in the entire halo of the galaxy. Let's say 60% of them are in dust, which is the maximum you'd see in the Milky Way in the densest regions. And this is our upper limit right here. So we're seeing that a lot of observations are at or above this upper limit, especially like all of the alpine sample seems to be almost above this upper limit. So this kind of suggests two things. Either the dust masses are overestimating, classic theorists, the observations are wrong, or we need a top-heavy IMF. I'm actually going to try and argue a little bit that it may be the first case. I have reasons to say this. I'm not just going to say this and leave it. Namely, there's one parameter that our estimate of the dust mass is really sensitive to, and that is the dust temperature. So this is how the general relation when you take your flux density, you measure to your dust mass, you infer from it. You get this beta parameter, which is from the chemical composition of the dust population, stardust geometry. It's a bit complicated. And then also you have this kind of fitted dust temperature. Now this isn't a physical dust temperature, it's really a fit to the SED. So don't think of it as just purely like a physical dust temperature. But it's really sensitive to this assumption at high Z because you're no longer in the Rayleigh-Jean approximation limit, and so this doesn't scale linearly with dust temperature, but it's like an exponential. So many observations actually assume the dust temperature. It's just an assumed quantity, and it's around 25 Kelvin, which is what's done with the Alpine survey, and many of the singular observations too. And this is what's assumed at middling redshift, so like 1 to 2, but it may not be the case at high redshift. The temperature may be quite higher. And we actually have the Rebels estimates. The reason why they're quite a bit lower in the Alpine, one of the reasons is they have this novel method of kind of decoupling the dust temperature from the dust mass. And they get estimates of the dust temperatures between 39 and 58 Kelvin with an average of around 50. So they are saying that the dust temperature may be twice as much as at least the Alpine survey is assuming. And the author of this, Vigo, went back and recalculated the Alpine dust masses, and they found that both the dust temperature is quite high, again around 50 Kelvin, and they get about a factor of 7 decrease in all the dust masses on average. That puts them better in line with the Rebel survey and in line with our enhanced model. So with that, I'll just leave my summary slides with saying that maybe the observations are overestimated at high redshift, and also high redshift is really great for testing dust theory as well.
Questions? Richard?
More of a comment, but regarding the dust masses, as I may mention this at coffee break as well, but recently, for the reason that you actually suggest, Hito Alhera from the Rebels team actually got approved ALMA observations in Band 8 to essentially try to constrain the dust temperature of all the sources in our IFU sample to essentially pin down the dust masses, which you say is a huge uncertainty here, and I think we completely agree. So,
Mm-hmm.
so progress is being made.
Yeah, I think you have been quite generous in the sense that there is a hard limit. You can't put more than all metals in dust. And in some of these cases, I've seen dust to stellar ratio of 0.1, which means that these galaxies should have a metallicity of 10 times solar. So clearly there is something probably on the observational front that is going on, because you have the metallicity of these galaxies, and typically we are all about 0.1 solar this ratio. Oh, sorry, yes, 0.1 solar. So I think there is an issue of 1 or even 2 orders of magnitude in the dust masses, or maybe it's in the stellar mass. I'm not sure.
When do you turn on your first supernovae?
When do we turn on the supernovae?
Uh-huh.
It's just naturally, this is fire, so when the stars form, and the supernovae turns on around, was it a few million years after the first star formation? But yeah, so it's just star formation is tracked, and the supernovae happen with the stars, solar populations that form in the simulation. So it isn't like the turn on would be just whenever the first stars form in the simulation. First.
Thanks.
Robert? Okay, thanks. So I think that makes total sense. The mass-weighted dust temperature should be about 25 to 30 K, but that's different from the dust temperature that you would need to use if you say, let's say, the peak temperature, or if you want the dust temperature that gives you the IR luminosity, right? And so, unfortunately, that's always a bit conflated, and there's just a single dust temperature, and you read it somewhere here, or this dust temperature, and then you use it there. So I think people just have to be very careful, and I think this makes total sense. So from previous fire simulations, we find, for instance, that we can have a redshift 2 and a redshift 6, dust temperature of 20, a mass-weighted dust temperature of 25 to 30 K, but then if you go to the peak temperature and so on, this can be 60 K, it can be 80 K, so it can be very different.
Yeah. So we talk about this in this paper. This paper will be released in about a week or two, and yes, we talk about this and about this issue of this. People aren't very careful with what they call dust temperature, and the way you measure your dust will change this dust temperature. So for some of these, like the Alpine sample, I think the Alpine sample is another re-estimate where they get some mid-infrared measurement with Herschel, and then say that's a higher dust temperature. That's an entirely different dust temperature that you're fitting to that.
Okay, more questions? Maybe a quick one.
Very quick. I'm so stupid, but I would think that the cosmic background radiation at Z of 10 is already 10 times hotter, around 27 degrees, and so I'm just wondering, is the background radiation an issue at all, whether it's UV or in this case cosmic background radiation?
You do have to factor in the cosmic background when you're determining things like dust temperature.
You say you don't care about it, or
you do need to, yes,
you
because they can't. Yeah, it can be getting near this temperature, like the lower temperature we think of dust just locally. Yeah, so we don't actually calculate dust temperature, but that would be follow-up for using things. We're already looking at using things like rate of transfer, like SIRT.
Okay, let's thank our speaker.